All right, so I think I can begin this sort of session right now. So first and foremost, you guys can hear me, right?
Yeah, we can hear you well. Thank you.
Okay. Okay, so first and foremost, my name is Amila Alexandar, and I'm a lecturer here at the Sri Lanka Institute of Information Technology, commonly known as SLIIT. And mainly I specialize in this field known as mechatronics, which is like a field combining, the word mechatronics itself is a combination of mechanical and electronics. So it's a field that involves lots of hardware and alongside software. Usually in fields, in the fields we had in the past, it was just either software or it was just mechanical. But nowadays, you require a combination of both these two fields in order to kind of develop these modern sort of systems and applications. So most of the systems you see on this slide, even, for example, like this drone, for instance, relies on a combination of both the hardware and software. So you can probably imagine there needs to be some kind of controller in order to spin these motors in the exact speed required so that this doesn't flip over, right? I mean, it doesn't have any steering wheel or doesn't have any like doesn't have any wings or anything. It uses just these four motors to go up, down, left, right, rotate, and everything. So you must imagine there has to be some kind of a system which involves software, which takes readings from the environment and which computes all these required parameters and sets the drone at a specific height, for example. All of these features need to be integrated into what's known as we call it in the field an embedded system. So we'll have a look at these what this is about. Um, okay, so as I mentioned, in this embedded system, it relies on mostly what's known as a microcontroller. So we'll get into what's known as a microcontroller later on in this topic. But for now, we'll just speak a bit about engineering first. Because in order to develop these systems, you kind of have to think like an engineer. So that's what I'll start the session with. So just a little bit about myself. I'll just do a small introduction about me so the session kind of has some context to it. So I obtained my bachelor's from RMIT University, Australia, and I do have a master's in software engineering as well from Kingston University. And my passion is basically, what I've been talking about is programming and solving hard problems, mainly problems which require both the application of hardware and software seamlessly. So, just looking at these images that you see on the screen, the first one, it looks a bit messy. That's because it's kind of a prototype, but this is the kind of bread and butter that I work with when developing these systems. And the bottom, you can see what's known as the infrared sensor. Each one of these black things you see here is a kind of infrared module that emits a light. And if there's an obstacle in front of this light, it sends out a specific signal. In this case, this also has a special feature of detecting black and white colored surfaces because that's a property of infrared radiation. We'll kind of get into these topics later on, but this is just kind of example. Okay, so in today's session, we'll be covering a couple of things actually. So this is, as I mentioned, we'll start with a bit of engineering and we'll talk about what setting expectations means here. in an engineering context. And we look at this engineering process and how we can kind of develop a mindset in order to set what's known as requirements for our given project. So if we have a task given to develop a certain system, we have to consider things like the cost, the reliability, how long we want this system to last, and certain things like if this should be fast, other things like that. So there's always this thing known as a trade-off, and you can't have everything. You can't build a system that's cheap, that works really well, and that's ultra reliable. So there's always a trade-off whenever you develop one of these systems. So that's what's known as like the engineering process, where you have to kind of prioritize a certain thing above another. So if you're building something, let's say related to maybe a healthcare system, you probably want to focus more on the reliability aspect and things like the accuracy of the data rather than the cost. Building a really cheap healthcare system, a small healthcare monitoring module or something, you don't want to become cheap here because that could pretty much end someone's life or put someone's life in danger. So that's why you have to consider this trade-off and consider what you really need to focus when you're developing a system. So we look at an example, the James Webb Space Telescope, in order to just kind of get a feel into what they have prioritized. And we'll go into the actual microcontrollers and what they're about, including a bit of electronics. And there's going to be like a small practical session as well in virtually using this software known as it's VOCV, which is a website on the browser. It's actually a simulator you can use for ESP32s, microcontrollers like Arduino and all these other components. You can add electronic components like resistors and LED lights and even sensors and just kind of simulate them virtually before actually making them on hardware. Okay, so Proteus, we won't be going into that, right? Okay. All right, so expectations versus reality. Now, I'm not sure exactly what kind of background everyone here is coming from, but in this kind of setup we have, we need to kind of set our expectations right. So at first, I mean, when you're given a certain task, what we tend to do is we develop a kind of prototype in our heads, a kind of soft model that we think that we might be able to develop. But the thing is, we're not actually sure until we gather the components, connect everything together, and power it on. We're not sure until then if it will actually work or not in the field. So this is uh, a major thing that you have to kind of consider when you have these hardware components into play, because hardware is really unpredictable. A loose jumper wire or connection, maybe a short circuit, or maybe a resistor gone bad, a capacitor gone bad. All of these things are really unpredictable and they might just ruin your entire project before you can actually even implement it. So you have to set your expectations right. Now you can see on the screen there's an image of what you can kind of it's known as a mobile robot, has four wheels, and you can kind of see there's these electronic components in the middle, a second floor, and a set of like motor controllers. Now, this is the design we draw on SolidWorks. This is what we intend to make, but oftentimes reality is quite different. So, as I mentioned, we begin with an idea. We start saying, let's do this thing, let's do that thing, let's put a bunch of motors, four wheels, it's going to look cool. We can put different speed ratings, control this with a remote control, all these different things. But the problem is actually implementing this into reality becomes a significantly hard challenge. I mean, unless you have the budget. I mean, if you have the money, then pretty much you can solve most of these issues. But the thing is, most of the time, you're not going to get an unlimited budget and you're going to have to be restrained with certain constraints. So the challenge is kind of identifying what works and what doesn't work and what gets the job done. So these three things are the things that you kind of have to look at when we develop a practical hardware and software system that we intend to use in the field. And a simple question here I'm asking is, I mean, if you're tasked with making a simple robot that follows a black color piece of tape pasted on the ground, is that what we intend to do in the lab? Or do we plan to do something or make a robot which travels on another planet? So these two different things have vastly different requirements. I mean, the cost aside, reliability is one major thing. We'll speak about reliability later on as we go through these slides, but you can probably imagine if we have a robot in front of us, something goes wrong, we can just pick it up. We can start fixing around with it and kind of make it work again. But if we have a robot kind of on Mars, there's no way to just go there and fix it. So this system has to be kind of at least almost 100% reliable. So that's what setting the expectations is all about. So as I mentioned, I mean, it starts with this initial concept that looks something like this. But the thing is, in the end, it kind of ends up looking a little bit different. The thing that we thought that we could make ends up becoming slightly different due to the actual practicality and implementation of this system. Okay, so that was just an example. So you can probably understand, I mean, in here there's 4 wheels, but as we move to this like final design, there's only 2 wheels followed by what's known as a caster wheel in the front. I mean, just in short, I'll explain what this is all about later on, but you can probably imagine having 4 wheels is not really practical if you're doing a small task of just moving a line following robot along the ground. So 2 wheels is enough to do this task, and it's plenty. And there's also a couple other things that you can notice here. I mean, inside the black kind of box we have here is where the actual hardware electronics microcontroller exists. On top of this, you can see a kind of a camera module, and in front is an ultrasonic sensor. So later on, we'll actually look at how we can actually use these sensors and these sorry, not the camera module, but we can have a look at how we can use these sensors on a basic level on this website that I mentioned before, known as walkme.com. Okay, so moving along, here's another kind of example where we have our expectations, where we plan to build this super cool looking portable weather station design. You can see it spinning and everything, and it has this display, all these cool looking buttons and everything. But reality kind of hits different because this is kind of what it ends up looking. But the thing is, this isn't the final design. It's an actual prototype. But along the way, this is a key component that you have to make in order to kind of identify the actual problems that you might encounter in the field. For example, having these buttons and everything, they look ugly right now, but that's the basic implementation of this system. And we probably have to like code different logic so that these buttons do different functions on this LCD display. But doing all that stuff actually requires implementing a functioning, at least a basic prototype. Because without this hardware, we can't simulate everything in a way such that it will reflect what you'll actually expect to see in the field. Okay, so this is the actual like version of the weather station that we kind of developed. And you can kind of see it slightly mimics the kind of GIF that I was showing before, but it's a bit thick. You can probably see that it's a bit large. I mean, that again, that's like a practical implementation of mostly it's the cost actually, because making everything small requires a significant amount of uh, capital. And in this case, since this is a kind of a final year project, it has we had a limited budget. But you can kind of see the basic functionality like the SMS notifications and all these other things are working to a certain level. But practically implementing this, let's say in the hundreds or in say thousands, becomes a completely different challenge. Because building one item is quite easy actually. You can design a single item to work really well. You can design it with pretty much a single case and all these things. But the problem comes when you have to design, let's say, the problem comes when you have to manufacture maybe 100 or 1,000 or 100,000 units. That's when things and the engineering process actually starts uh, having a huge impact on your actual product, because this needs to make money at the end of the day. So having a product that is efficient in terms of the cost is quite necessary. Okay, so that's just a small example. Now, for later on, I just want you to kind of look at some of the basic features we have here in this weather station, actually. So on the home screen, you can probably see it measures the temperature, the humidity, and the pressure. So all of these things are measured on this device itself. Underneath this black shell, we have what's known as sensors. And sensors are pretty, I mean, the word sensors is a pretty basic word, but um, if you go into specific kind of how these are actually made, these are small electronic components that have the ability of detecting a certain environmental factor. In this case, it's the temperature, the humidity, the pressure. And if we move along, we can probably see some other ones like the carbon monoxide level, the soil moisture, luminosity, and all these other different things on this device. So we'll have a look at what these sensors are about in the slides later on, but this is just a small example of what an embedded system kind of looks like. Okay, so moving along, back to looking at the engineering aspect of these systems. So as I mentioned, engineering is not just developing something cool and complex, it's a trade-off. We always have to think about the cost of things, how reliable we want to make them, and other things like if you want this product to last a long time, all these different things we have to consider when we're developing a certain product. So let's say that someone tasks you with building a small kind of four-wheeled robot, mobile robot that we saw in the previous slides. So you can probably imagine it needs a processing center or centralized location to compute data. And you can imagine there's always a choice. You can get a, I mean, if you wanted to, you can find a radiation hardened CPU with auto correcting RAM. But the problem is you can't find this nearby in the town next door. Here, Malawi refers to a place that's close by the way. I mean, you can do that, or you can go with an Arduino. So you have two options here. One of these is super expensive, super unnecessary. The other one is kind of more practical. And in this case, most likely it's easier to go with an Arduino because it costs like 1,000, or in Australian dollars, it costs like maybe $5 Australian. And that option is quite beneficial rather than say, going for like a expensive CPU that has error correcting RAM and everything. But at the end of the day, again, it's a matter of our requirements. One of the biggest thing is, can my design afford to fail? If you're building a simple robot that's expected to travel on the ground for, let's say, on the ground in the sense, in a closed environment, in a room that we have access to, the design can afford to fail. I mean, if it breaks, we can pick it up, we can plug some wires in, we can solder some components, and we can do a couple of things to get it back working again. We can fix it. But the problem comes if we want to change this and actually implement this on a, let's say, a different planet. So implement this on a different planet has a completely different set of requirements because we are tasked with making this incredibly reliable. We can't fix it because we're not sending people to Mars alongside the robot. Okay. So as an example, I mean, just as a simple example, on the Earth, if we have a loose connection, all it takes is just walking over to the thing, plugging it back in. It barely costs anything. But if we have a loose connection on Mars and we plan to fix it by sending someone there, it's going to cost at least $1 billion to send a person to Mars, plug in the wire, and get them back again. Because there's costs like the rocket and sending them and all these different things. So that's kind of where the requirements part comes into play. Okay, so moving along, we'll have a look at this space telescope known as the JWST or James Webb Space Telescope. So this was released, this was launched, I believe, in 2020, and it was made to kind of look into the earliest time in our universe. What I mean by this is it can see far into the universe, which means it can kind of look into the past. Or in this case, it can look at the stars that were created approximately 13 billion years ago. So that's why this system was kind of launched. And it doesn't look like a normal telescope. You can kind of see it has all these like silver color fins, this gold color kind of frame here, and a couple of components at the bottom. And briefly, I mean, I can just explain what this is about. You can kind of see it resembles kind of a satellite dish, probably means it's collecting some kind of information there. And this silver color thing that you see is known as a sunshade, and it keeps the telescope from overheating from the sun. So this gold color section is facing away from the sun, and this silver color thing is protecting all these components from the heat and exposure of the sun. Main reason is because it's detecting infrared radiation, kind of similar to our design that we saw in our first couple of slides where we had these infrared sensors. It's working with the same bandwidth of light, but in this case, it's collecting probably approximately 10 million times more light than your average Arduino sensor. So coming back to the topic of requirements gathering for the engineering and developing a real-world system like this. So if we consider this space telescope itself, there's over 300 single points of failure. What this means is, if a single system or single component of the telescope fails, that means the entire design is pretty much, it goes into the garbage. Because a single point of failure means that it won't be able to look into the cosmos, it won't be able to capture pictures of stars, and it won't work. And the problem is, this is spinning around the planet approximately 1 million kilometers from us. So it's not like we can just send a rocket, send some space people, and get a drill and fix it, because it's an incredibly tough challenge. So here there's like a 300 single points of failure. How do people, I mean, actually spend 10 billion US dollars approximately, and with the knowledge that it will work? So aren't these people scared? Aren't these people worried it's going to fail? Aren't they worried about spending 10 billion US dollars on something that might fail and will waste them $10 billion? So this is kind of a question that you have in engineering, where you have to ask yourself, is it worth it? And in this case, this is a scientific community, and to them, it is worth it. And with the right people and with the right kind of mindset and engineering discipline and principles, there's an approach to making this feasible. So the question is, how do you build something to work 100% of the time? The answer is, quite frankly, you can't do this. There's no such thing as a 100% reliable system. You can try and try and try and try and make it almost 100%, 99%. But the thing is, with hardware, there's always a matter of unpredictability. For example, if we have a CPU, CPUs on the planet, I mean, on the surface of the planet, the ones we have in our computers, aren't affected by what's known as cosmic radiation. So, cosmic radiation in this sense refers to uh, particles emitted from the universe traveling approximately close to the speed of light. What happens is these particles or these protons, ions, they come and collide with the physical structure of the CPU. And without our knowledge, a 1 becomes a 0. Or in other words, it's called a bit flip. And when this happens, you can probably imagine a system which works with ones and zeros. And when ones, and if a single bit is kind of flipped, the entire code might just crash. So these cosmic particles that I mentioned, they don't come in contact with our computers that we have on the Earth. But out in space, this is expected to encounter lots of them. So they have to develop the system so that these cosmic particles can't affect the actual CPU or the processor of this telescope. Okay, so in order to kind of develop such a system like this, the only way is to pretty much test, test, and test over again. Pretty much do every single test that you think will happen and make sure that it passes, and also make sure that there's a plan B in case something goes wrong. So that's what building redundancy into your system is. The thing about redundancy though is if we could do this, I mean, if we could do this to pretty much anything, like let's say a car, and we had, let's say, we wanted to build a 100% reliable braking system in the car, the common ABS system on your car, it might fail. There's always a chance it might fail. It's not 100% reliable. So let's say we task an engineer, build this more reliably. They might think, okay, let's go ahead and add a second set of calipers onto the brakes. Now what you have done is basically double the cost of the braking system, and you have, even though you double the cost, you don't double the performance necessarily, because the single brake that we have on our day-to-day cars, it's probably going to function for at least 10 years without any failure. So anything beyond that, anything beyond tuning that to a more higher state of reliability, it requires a second set of brakes, but we won't be actually using them for the majority of the time, even though we have spent twice the amount of money developing the system. So again, money is a key factor here. If you have an unlimited amount of money or large amount of money, redundancy is an actual option. That's why we don't have two sets of braking systems in a car per wheel. We have a single brake per wheel in a car because that's pretty much enough for 99.9% of all cases. And developing a system for that 0.01 is going to just cost you money, effort, time. It's going to make the vehicle more expensive, and all these problems are going to come. But this 0.1% in the vehicle is much more different than the 0.1% on the James Webb Space Telescope. So in this case, they're probably going to develop not just two, maybe three or four redundant systems just in case something goes wrong and everything fails, because they can't afford to spend 10 billion US dollars and have the product fail at the end of the day. So that's what building redundancy into your system is like. Okay, so if we have a look at this person here, his name is Dr. John Mather, and there was this YouTuber, Smart Everyday, who did a small interview with this scientist. He's kind of the lead project scientist of the James Webb Space Telescope. He's kind of in charge of the project and the kind of the team lead. And when the YouTuber goes ahead and asks this person if he's not scared about losing the entire project, because he's the head of the project. I mean, think about the how much pressure he must feel if the project goes wrong. If something goes wrong, he's probably going to get fired because he's the project head and he lost $10 billion of money on some kind of failure. No matter how unpredictable the fail is, someone is always going to argue, you wasted $10 million on this thing. Why did you do that? So this YouTuber goes and asks this person, isn't this a really anxious moment? The moment I'm referring to here is the launching of the telescope. And he replies with, no. And he says he doesn't get anxious about stuff he can't deal with. And the YouTuber asks, can you tell us why? Because and then he goes ahead and replies with, I know that we're doing the right thing to make the best possible plan. So what this means is that he knows that he has taken all the steps, he has done everything he can, or he has tested it as much as possible, thought about all the different kinds of scenarios, and worked out the system so that there can be no kind of unhandled errors. This is an incredibly difficult task, but by testing over and over and over again, he knows with a good amount of self kind of reliability that the system is not going to work because they put as much effort to it as they can. And if something does go wrong, they can kind of still be at a peace of mind because they did as much as they can to kind of make sure the error didn't happen. So that's what you kind of have to do when you build such a system. You have to test it such that beyond a doubt, beyond a doubt of any errors that we expect, the system will work. Right? So that's just an example for practical kind of uh, hardware and software challenge that you see here. And here you can kind of see the actual people in charge of launching this system. So it requires, I mean, a team of people. It's not just a single person creating these telescopes or these engineering projects. It's a team of people and they're really smart people. So this is just an example I just wanted to show you because everything that you see, I mean, all these amazing things that engineers and scientists build, they all start with people and a remarkable group of individuals. Okay, so that's just a small introduction and kind of an example into the engineering side of why we build reliable systems and why we do them, how we do this process. Okay, and the actual output of this. This is a picture that the James Webb Space Telescope took. It's known as the cosmic cliffs. And at the end of the day, this is what everyone is after. This is the actual final output that all the hard work, all the effort everyone puts in, this is what it's going to generate. What you're seeing before you is a cloud of gas and dust, and a couple of stars that are probably millions of light years away that somehow humans have managed to capture using their talent of engineering and using their skills. So, I mean, if any of you are fans of space, you probably have seen this picture. And getting pictures like this of the universe when we are stranded on this simple kind of planet in the middle of like a galaxy, it's quite remarkable. And so this is what engineering and the scientific process and everything, at the end of the day, this is the output that we expect to get whenever we build a system. No one sees the electronics, no one sees the software, the code, the hundreds of thousands of hours of work that went into the project. But what they do see is the actual output. And the actual output in this case is quite remarkable. And even if you're building something small like a weather station, the actual output is what everyone else sees. But what you see and what you know is that you spent countless hours working on the software, getting things right, making sure the cables are connected, making sure the code compiles and runs, making sure that errors don't happen. And all these different things are what we as kind of engineers have to take into consideration when we are developing such a system. Okay, so that's just a kind of introduction into the aspect of engineering. Now we can actually move on to the kind of electronic side of things. So let's say, I'll just check if this is working first. Yeah, okay. So we might draw some things. I'm not sure what we'll draw, but we'll might draw some things, right? Okay, so that's about engineering and the challenges that come along with that. So let's dive into the actual topic for today, which is electronics. So, I mean, when we speak about electronics, we have them pretty much all around us. So, I mean, what you're looking at right now on the screen is an electronic component that is powered by DC voltage. It has hundreds of resistors, capacitors, transistors, power management circuitry, different types of integrated circuits, and all these small components that we take for granted. But at the end of the day, what all of these small components allow us to do is view a presentation from 10,000 kilometers away. So if you're watching this in Australia, that's what you're pretty much doing, right? I'm doing this presentation in Sri Lanka, and through this application of electronics and all these different components, you're able to watch something that's being done 10,000 kilometers away by using these what's known as these electronic components. So we'll have a look at kind of a basic introduction into what this electronics is all about. We'll have a look at the equation famously known as V equals IR, kind of an example to practically understand this. And we'll also have a look at different sort of things like AC, DC voltage and why we use AC, DC voltage. And finally, we'll actually get into the topic of microcontrollers. Okay, so electronics, as you imagine, as you know, they work with this thing known as electricity. So that's what electronics work with. And the main basis, you can kind of divide this into two major kind of factions. One is known as the analog world, and the other one is known as the digital world. Now, analog in this sense, you might think that we are referring to some age-old technology from the 1900s, but that's not always the case because analog circuits do become important when we have even in modern applications. But most of the time these days, everything is pretty much digital or ones and zeros. So that's kind of what electronics is divided into. And if we talk about the actual hardware side of things, the actual kind of components we have. So most of these things probably you might have heard of as things like resistors, capacitors, transistors, diodes. And these are the kind of the basic components that make up all these larger components like integrated circuits, PCBs, and even larger circuits than that. So they're pretty much all around us, and we'll have a look at the kind of theory behind them or the principles of how everything works. So you must have seen back when you were in school, we draw this, we used to draw this graph, right? Maybe we have V, we have I, and it looked something like this. So this is what's known as Ohm's law. And back in school days, I mean, pretty much we learned this, but we didn't kind of get an understanding of how this actually works. We didn't get a kind of intuition of how this actually works, what this means, and how we can kind of work with this. So if we take a look at this equation, V equals IR, probably know that V stands for the voltage, I stands for something known as the current, and R is the actual resistance that we have in our system. And for some reason, we were taught in school that this is kind of directly proportionate to the resistance. But we don't necessarily know what this means. So if you have a look at this image, actually, this kind of helps you understand what this whole voltage and resistance situation is kind of about. So if we look at a more practical example of, before that, let's have a look at this picture actually. So you can see there's this, the voltage, or this guy in yellow, is kind of pushing the ampere guy through this constricted section, and the actual ohm or the resistance is preventing the voltage from pushing the current through this restricted section. So you can probably kind of imagine if we have a kind of wire like this is a wire, it's a general everyday day-to-day wire, and along this wire flow these electrons. So the electrons themselves don't move, but they kind of push against each other and cause this effect known as current, or in other words, amps. But the amount of pushing that occurs, the amount of potential that these electrons are pushed with, or the amount of force that these electrons are pushed with, is determined by what's known as the voltage. So if we have a higher voltage, large voltage, these guys are going to get pushed really hard, and it's going to kind of generate a high amperage. But what we don't see here is, depending on the material of the wire, these electrons might flow fast or they might flow kind of slow. So this depends on how much resistance or how much ohms we have in our system. So that's why we see this red color guy kind of restricting the flow of current that the voltage creates. So if we have a general kind of basic system, how can I draw this? So we have a resistance here. Generally, the resistance is kind of a fixed value. I mean, because it's determined by this hardware component. The voltage itself can go up and down because it's kind of a thing that it's a potential difference. You can change it. The amperage, though, we can't just change it on demand whenever we like. It depends on the actual voltage. So the amperage, as I mentioned, is the flow of these kind of electrons through this wire. How the amount of potential that we pass into the electrons, or the amount of pushing force that we give into the electrons, is determined by the actual voltage. So if we give a higher voltage, these electrons are going to go much faster, and it's going to create a higher current in our system. If you give a low voltage, electrons are going to go a little bit slower and create a lower amperage in our system. For example, if you ever have, let's say, charged your phone. Phones are actually quite different than this example, but you can probably imagine if you plug this phone into a computer, It is generally going to charge with what's known as 5 volts at 500 milliamps. This is the amount of current that's going, and this is the voltage. Now, theoretically, if we increase this, let's say 10, we would expect this value to go up as well. But the thing is, with electronic components like the phone, that's not going to happen. But that's kind of what I'm talking about. So your phone is going to charge much faster if you have a higher voltage, because the amperage or the amount of electrons per electrons moving is going to increase. So that's kind of like a visual understanding of this Ohm's law. Okay. So moving along, if we have a look at these actual components of electronics, like the resistors and capacitors, diodes, different small other components like LEDs and transistors. So I'll just kind of do a brief kind of explanation into what these are. So as you know, resistor, it's going to limit the amount of current moving through your system. So if we have let's say a bulb. So this is our bulb. Currently it's illuminating, let's say at a value of 500 lumens. It's connected to a voltage source, let's say of 10. Now, if we want to reduce the brightness of this, we have a couple of options. You can either change the bulb, you can buy a new bulb and have this bulb have a larger resistance value. That's one option of getting this lumen count to go down. Second option is to increase the voltage. Because as you increase the voltage from 10 to let's say 20, you're going to push these electrons much harder through this wire. And it's going to go faster kind of through this light. And it's going to increase this value to let's say maybe 1,000 lumens. So that's one way of increasing the brightness of our light. A second option you have of kind of reducing this amount of light that you can use here, instead of actually changing the voltage or anything, you can go to the shop and buy what's known as a resistor. And this resistor isn't going to affect this guy. It's not going to change the voltage, but what it is going to do is it's going to slow these electrons down from flowing through the wire. So just like with this example we saw, adding a resistor kind of constricts the flow of current through our wire. Even though the voltage guy is trying to push the same amount of electrons through the wire, the resistor that we drew here in blue, it's going to restrict this flow of electrons, thereby reducing the actual luminosity of the light. So that's one way we can reduce the luminosity of the light. And these other components like the capacitor we'll discuss in the example itself are used to kind of affect the voltage. And these things that you see here, like the diode, for example, the diode is used to ensure that our electricity flow only works a single way. So this becomes incredibly useful when you're designing certain electronic components and you don't want the electricity going the other way. Right? So that's what a diode is doing. It ensures that electricity only flows in one way. So let's say that we have a kind of a battery like this, and we connect it to if this is, let's say, some kind of electronic component, and this component is connected such that we have plus and minus like this. So you can imagine this as, let's say, a remote even, or remote control in the sense your everyday day-to-day remote control that you have on your TV. we put in AA batteries inside it. There's a plus and a minus. And this is the kind of diagram that I've drawn to show that. Now this electronic component works when the plus is here and the minus is here. And if you do this right, you kind of know that the electricity is going to flow. The electrons are going to flow this way and the actual electricity is going to flow like this. And the electronic component works. But what happens if we reverse the polarity? Or in other words, if we kind of switch this battery to the other way, electronic component is going to expect the plus and minus, but we have connected the minus and plus. So what's going to happen is we connect plus to minus, and what happens usually is this guy, it goes boom, and we pretty much have a burnt piece of electronics. So what you can do to prevent this is you can add what's known as a small diode, which allows the flow of electricity in a single direction. So when the battery is connected like this from plus to a remote like this, from plus to in this orientation, the electricity flow just, it goes fine. There's no issues with it. For some reason, if we connect the battery like this, and this is our remote now, electricity is going to want to flow in this direction. But the thing about this diode is, it's not going to let the electricity flow. If you have a look at the circuit diagram of this diode, it looks pretty straightforward actually. It's like a play button or an arrow which shows which direction electricity can move through. If electricity starts coming in the other way, it's going to hit this kind of wall looking thing and it's not going to allow it to flow. So that's just kind of a basic example of why the remote controller you have in your house, it doesn't burn every single time you switch the batteries polarity from plus and minus because they have diodes inside. So it's not just a matter of protection itself, but that's just a simple example I'm giving for what diodes are. And LEDs are another completely different kind of thing where we take this technology completely for granted. There's actually this really good video on, I think YouTube, I think probably not going to have a chance to view it now. But if you have a look at the story of the blue LED and just kind of look into this, the actual video by Veritasium, I believe. This one, blue LED breakthrough kind of by Veritasium. So this guy is the presenter I'm looking for. If you have a look at the actual story behind this blue LED, it's quite remarkable. And it kind of helps you kind of see how like amazing all these technologies. And we just take it for granted every single day, every single time we switch on a TV. We don't even think about it, but it's controlling millions of these LEDs inside the circuits. So that's just a practical kind of example to help you understand that. So an LED, I mean, you can probably understand it's when we say LED, we probably think about the bulb that we have at our house, maybe, where we have LED bulb like this, and it's giving light to the room. That's one kind of thing that we have. But what we don't think about is the LEDs we have in our laptops, for example. So, I mean, an average laptop has a set of, it's a panel, and depending on the laptop type you have, depending on the technology of screen this is using, you might be working with around, let's say, uh, this many LEDs. So this comes up to a huge amount, and this electronic system or the electronic controller has to control at least this many number of LEDs. So this works around, I think, around 2 million or so LEDs, right? Yeah. So we don't take, we just take all of these systems for granted, but they're applicable in pretty much everywhere in our day-to-day lives, not just in the LEDs that we see in our house. Okay, so those are just a couple of examples for the components we have here. And the last one is actually the most remarkable component, the transistor, or what the basic, the foundational component which made all of modern computing possible. So the transistor itself was developed around the 1950s, and after this only started the technological revolution. Because in the 1920s and let's say the 1800s, you didn't have smartphones, you didn't have TVs, you didn't have computers, you didn't have anything because this guy known as the transistor wasn't invented yet. Only after this did all these technologies come. So you can probably imagine with the start of the processor, we got like hard disks and we got all these different technologies. We developed monitors, we developed smartphones. We now have like ChatGPT systems which literally kind of simulate intelligence. And likewise, all of these systems were brought about by this simple component known as the transistor. It's a simple kind of component with three pins, unlike an LED which has two pins. A transistor has three pins. And the basic foundation behind how this works, we might go into this if we have the time, but we'll see in the slides after that. So these are just, I mean, on the surface, they look like basic components, but after my kind of explanation, you can probably understand how significant they are to a modern world, even though they are so foundational, right? Okay. So moving on, now electricity. This is the basic of how electronics are working. It's that symbol you see here. There's different types of electricity. So what we see in if we put our finger into the plug at our house, probably going to die. But what this electricity is what's known as AC current. You might have heard in Australia, it might be different, maybe 115 volts. In Sri Lanka, it's 230 volts. There's different reasons for this. Again, one of them is cost. Usually, cost is the driving factor for most of these things. Sri Lanka works with a higher voltage, which is it's it's um it's cheaper for the country, but the problem is it's not cheaper for uh, human life, right? I mean, it's gonna if you get shocked, you're pretty much gone. So that's why some countries like Australia work with maybe it's 150. I'm not sure exactly if it's 115 volts. Maybe it's 200 there as well. But for a fact, I know that in countries like the US and Canada, they have voltages from 115 to kind of 110, 110, right? So again, the reason is because it's safe on people, even though it's a bit cost ineffective. It's not cheap, right? So we'll discuss, I mean, how this actually works in slides later. But that's at the end of the day, the trade-off that they have chosen. It's the safety versus cost. Okay, so AC versus DC current. So I mean, AC/DC is the name of a band, but it's also, you might have seen these diagrams. AC current looks something like this. DC current just, it's a straight line pretty much. And these axes for these graphs are the voltage and the time. So for in the DC case, you can probably imagine it's steady, it's fixed, and it's kind of constant throughout time. This is 5 volts. It's going to stay the same value 1 second from now, 2 seconds from now. It's going to be 5 volts continuously. But if you have AC current, it's not going to stay the same. It's not even going to stay the same polarity. So in this case, it's going to be 5. In here, it's going to be -5. So that's like completely different from our logical kind of intuition. So in the first second, it might be 5 volts. In the second, it might be -5 volts. That's like completely different from the DC situation. So you can probably imagine, due to this kind of changing nature, where it's always going plus minus, this is probably not suitable for general electronic components that rely on, uh, general electronic components we find in our day-to-day lives, in our consumer electronics. Because, I mean, it's switching back and forth, the voltage plus and minus, and you can probably imagine it's not going to have the same effect that a smooth, stable line is going to have, right? So that's why we have DC working in our computers and in our phones, pretty much TVs, pretty much any electronic component we have the DC voltage. That's why you have to carry around this black color brick-like thing in order to charge your computers. It's turning the AC voltage into DC voltage. Now you might wonder if all our computers, if our TVs, it's a washing machine, everything is using DC current, why don't they just send DC current from the transmission lines? So what I'm drawing here is a transmission line. Why don't they just send DC current through these transmission lines? So we don't have to bring that black color box thing every time we want to plug in our computer to a wall outlet. We can just maybe plug it directly to the wall. So this is going to be plugged into the wall outlet. That's the wall outlet, by the way. So why don't they just use DC everywhere? Well, there's, I mean, again, it's an engineering reason that they have chosen. It's a matter of, in this case, practicality. Because if we have a look at how current is actually generated, current doesn't come from some guy pedaling a bicycle. It comes from, usually, in most cases, no matter if it's nuclear, no matter if it's wind generated, or if it's hydro generated, or if it's even a different kind of technology, like a coal power plant, what everyone or what this basic technology is doing is it's taking a kind of a turbine and it's making it spin around. No matter if it's nuclear or if it's hydro or if it's wind or if it's, let's say, what do you have? Coal. But all of these things are doing is just making a turbine spin, and the turbine is connected to a gadget known as a generator. And from the way generators are built, these output what's known as three-phase electricity, which in simple terms mean if you take just one of these lines, the output is going to look something like this. So it's going to output AC current from a generator. And if we had to convert this to DC, we run into certain problems in the grid. For one example, the generator we have here, it might be 1,000 kilometers from your house. So you have to connect this generator through the power lines, which might go for 1,000 maybe kilometers all the way to your house. And if you recall the diagram that we looked at before, where we had this, power lines have resistance. So all of these lines, they're going to have a resistance. And to push those electrons over 1,000 kilometers, you're going to need a large voltage. It's not going to be enough if you use 10 volts. You're going to have to use, like, let's say 10,000 volts to push those electrons through the power line, through the electricity, through the conductor material of these power lines, all the way to your house. And an easy way to kind of boost the voltage that we have, boosting voltage is, let's say, converting 10 volts to, let's say, 1,000. That's known as boosting. An easy way to do this is to use this component known as a transformer. This is a kind of circuit diagram we have. And the transformer, the thing about the transformer is, this guy is going to boost our current from, let's say, 10 to 1,000 volts using a simple principle of winding a wire. If we have here 10 times, the number of windings we have on this side is going to be, in this case, 100. So this is going to have 100 windings. This is just going to have 10. And by doing this simple thing, and by connecting this to, let's say, the same generator, you can now convert your 10 volts to 1000 volts using this component known as a transformer. And it only works with AC electricity. So the whole reason we have AC electricity through our power lines is because it's easier to kind of boost our voltage to a large value. And the reason we boost it to a larger value is because there's a theory in electricity. When you have a larger voltage over distance that's pushing the electrons, it's not going to waste as much energy as heat along this conductor line. So let's say that we have our electric kettle connected here, right? So that's our electric kettle. It draws 1000 watts of energy. And here we have our hydroelectric generator kind of making this electricity for our electric kettle. There's two ways of getting this 1000 watts. You can either do 1000 volts at 1 amperes, or you can do, let's say, for example, 100 volts at 10 amperes. Both of these are going to do 1000 watts. You're going to be able to charge your electric kettle, or you're going to be able to use the electric kettle just fine. Problem is, though, you have to send this over thousands of kilometers, and it's going to have a large resistance. When you have a large amount of amperage moving through a resistance, just like this image we have here, you can probably imagine this is the constricted kind of part. If we have tons of amperage moving through here, it's going to heat up the wire. It's going to heat up the wire, and this heat is actually wasted electricity. So by sending a large amount of amperage, 10 amps, let's say, you're going to spend most of the energy, you're going to waste it as heat. And you're not going to be able to do much with the kettle because you have already spent maybe more than that energy just sending the electricity through the wire. But one principle we have in this theory is, instead of increasing the amperage like this, what we do is we ensure that whatever amperage passes at a higher speed. So maybe we pass just 3, let's say in this example, circles here, but we send them with a much harder push than before. Again, a harder push in this sense means having a greater voltage level. So we give the huge voltage, push them harder through the line, and we have now a low amount of wasted heat in our system. So that's why we kind of have a larger voltage. That's why we need a boosted voltage in order to transmit our energy through these power lines. It saves energy and it saves money. That's the reason. Okay, so that's why we have AC and DC electricity through our wires and in the country. Okay, so that's the point that I made here. It's good for transmission, and DC is good for electronics. And you can see that the point that I made here is it can be transformed with transformers easily. That means the voltage level can be boosted from 10 volts to 1000 quite easily using this transformer component. I mean, if you look at the transformer, it's pretty much just a metal core, couple of metal wires winded. That's pretty much about it, right? It has not much advanced circuitry or components to it. It's just metal and more metal. So it's a simple component. But it has the ability of boosting the current from 10 volts to 1000 volts. which has the advantage of reducing the heat generation caused due to transmission. That's why we boost our current. Okay. And I mean, these topics, I think, these are they make sense, right? Okay. Okay, so that's kind of comparison between AC and DC. And if we take any kind of battery that we have, whether it's in a Tesla car or whether it's in the remote controller, we know that it's DC. If we take a standard battery from a remote controller, it's 1.5 volts. So that's the standard 1.5 volt constant voltage. Okay, so this is, we actually spoke about this topic. We spoke about this as well. We looked at this. And now we can kind of look at a practical example of how some of these components are used. So if you remember, we spoke about the resistor, we spoke about capacitors, and we spoke about diodes. So all of these things can be used in this simple circuit known as the rectifier. So this is what's known as a full bridge rectifier, and it converts the squiggly lines that we saw before. It converts this. Sorry, I'm going to draw this a bit better. It converts this into this, right? So it converts AC voltage to DC voltage. It converts the transmission line into electricity we can use in our actual electronic devices. And it looks like something like this. I mean, it's a simple circuit. This is what it looks like. And that's kind of, I mean, we can go into how this works, I think, but I'm not sure if that's actually necessary. But again, notice how these components here, the ones marked with this kind of play button and this line, allow the flow of electricity only in a single direction. So electricity allowed to flow in this way, but it can't flow that way, right? That's what it means. And in this case, you might be wondering why this line is, I mean, it's squiggly here and it's doing some weird thing here. So what's actually happening is it's kind of taking these crests and these troughs, and it's getting rid of this guy, getting rid of this guy and making it kind of like turning it around. Again, it's getting rid of this guy and it's making it into this guy. So that's why we have this bumpy sort of diagram here. And again, we know that by using something known as a capacitor, you can kind of prevent this rapid change and ensure it kind of smooths out like that, something like that. So by using a higher capacitor, you can make sure that your DC voltage is more and more steady, right? So that's just the use of a capacitor and a diode followed by resistance, I mean, here. Okay. All right, so that's just a kind of example of what DC and AC electricity is about. And here we have a transistor. I don't think we need to go much into this transistor topic, but for the sake of kind of explaining what this is about, this is the foundational component that we find in every single electronic, advanced electronic item that we have. So whether it's a computer, whether it's a smartphone, whether it's a laptop or server or anything, it's going to have couple, at least million of these transistors inside it. They don't look like this when they're inside the computer or the transistor processor. They have a different kind of physical structure to them, but nevertheless, the function, the basic function of them remains mostly the same. So you can find, I mean, in the latest kind of processors, you have like let's say we have We're talking about the Intel i7, latest generation of processor. You can expect to find, I think, close to maybe 10 billion of these transistors inside this device. And the number of transistors directly kind of correlates to uh, how much performance you get from this chip. So an i7 processor from, let's say, 2005 is going to maybe have only maybe 10 million transistors. But throughout time, throughout the evolution of technology, scientists have managed to make the transistors smaller and smaller and incorporate billions of them inside these smaller chips. Nowadays, the transistor gate size, or the actual transistor size that we can see, is close to 3 nanometers. It's known as the gate size, and this is what we are working with now. In the, let's say, 2015, it was maybe around 100 nanometers. But nowadays, it's closer to 3. So that's kind of what transistors are, and they help run all our modern advanced electronic components, like the processor and all these other different kind of components. That's what a transistor does. And if we look at the actual, working of a transistor from a simple kind of perspective, what it does is it enables the representation of a 1 versus a 0. Or in other words, it enables digital logic. Because at the end of the day, you've seen these ones and zeros everywhere, right? 1, 0, 1, 0, 1. You know that computers working on ones and zeros. The reason because it's 1 and 0 is because at the end of the day, you can either have an electric current, you can either have electricity, or you can either not have electricity. You can have either 1 or you can either have a 0. You can have electricity or you can have an absence of electricity. So this representation of the presence of electricity and the absence of electricity is done by the component known as a transistor. When you cram multiple millions of these transistors into a single chip, it's going to create a really powerful processor that we use. So working up from this transistor concept, we go to things like gates actually. You might have heard of things like the AND gate, the NOT gate, or the OR gate. These are sort of slightly advanced versions of these transistors. And by developing these components, we can do things like simple mathematics, which at the end of the day is what computing is all about, right? Because mathematics is what allows all of the things that you see on your screen to be computed. It, at the end of the day, it's a bunch of ones and zeros working across a small thing known as a transistor, right? Okay, so that's how transistors came about. All right, so we won't be going to the actual specific types of transistors and everything, but the basic thing you need to understand is a transistor works as a representative device. It represents a 1 and a 0. The actual function of a transistor is quite straightforward. Again, if you have a look at this arrow that they're using, this represents the flow of electricity. So let's say that we have a system kind of like this. Arrow is pointing this way, right? And so what we can do here is by setting this to 1, we can say, okay, allow the electricity to go. By setting this to 0, we can prevent the electricity from moving. So it kind of works as this common component that we use every single day called a switch. If we give a signal on to the switch, if we connect it, this guy is gonna say, okay, let's allow the electricity to flow. if we give the signal 0, we're going to say, okay, electricity can't flow from here because it's physically not connected. But the thing about the transistor is nothing moves inside this thing, and it works, in the time frame of nanoseconds, right? So it's not going to actually move any component or switch anything, but it's still going to have the same result in the fact that when we give 1 here, it's going to say, okay, let's have the electricity move. If we give a 0 here, it's going to say, don't let the electricity flow. So in other words, it represents a kind of a 1 and a 0. It works as a switch. That's how transistors work. Okay, so moving on to the actual Arduino and microcontroller side of things, we can have a look at what's known as microcontrollers in this topic. So microcontrollers, it's not too difficult to understand because if you look around the room, if you look out around the room you're in right now, you can probably find at least 5 different kinds of microcontrollers around you. So if you have a mouse on your desk, that itself has a microcontroller. If you have an AC in your room, that has a microcontroller. If you are wearing earbuds, those have microcontrollers. And if you have some other system like a projector or some kind of other device, all of these systems have what's known as a microcontroller. Again, you can probably understand from the word itself, it's a computing center, right? It's a thing that computes something. But the difference is, unlike an Intel i7, unlike an AMD processor or an M1 Apple processor, this guy is much, much, much less powerful. So if your Intel i7 can do, let's say, 10 trillion operations per second, your microcontroller that we find in a Bluetooth headset or in your mouse, it might be only able to do 100,000 operations per second. You might think that this is still a large amount, but when compared to trillion, it's quite slow. So it's much less powerful, the microcontroller that we have in our headset, the Bluetooth and everything. But at the same time, it's also much less expensive because the microcontroller that you find in your headset might cost a couple of maybe 10 cents. But the microcontroller or the day-to-day CPU that we have, the i7, it's going to cost around maybe close to $100. So that's a large, huge amount of difference. But the thing is though, if you're working with a mouse, if you're working with a Bluetooth headphone, this guy only needs to do one thing. It needs to be able to move the cursor. Your headphones need to be able to play music, maybe have active noise cancelling. It's just two different things. But your computer, on the other hand, your desktop computer or your laptop, it needs to do hundreds of things. It needs to go to Chrome, it needs to browse Facebook, maybe it needs to, open up the webcam, it needs to have the ability of having a Zoom meeting, or maybe, you need to be able to connect a mouse and all these things to it. It needs to do hundreds of things. So that's why it has such a powerful processor. But if your thing only needs to do two things or one thing, you can afford to have a smaller kind of chip that's not the i7, but much, much more less powerful. In most cases, it looks something like this. So this black color component you actually see here, it's a kind of a small integrated circuit, and it's a microcontroller. It does something really simple, but it does it really cost effectively. So again, if you come back to the topic of the trade-off of engineering, if our goal is to do something really simple, we probably want to reduce the cost. because we can afford to reduce the cost. I mean, because the thing we're doing is quite simple. And at the same time, the power consumption, I mean, all these other things also go down as a result. So this is the kind of main difference between, let's say, the i7, Intel i7, and what's known as this Atmega 2560 micro, in this case, processor. So this is kind of like the i7, but it's much, much less powerful. It has less processing power. It consumes less power, and it's much less expensive than the Intel i7. And again, there's different kind of things like how RAM and memory and all these things, they are arranged differently in these systems, but the basic goal is kind of the same, right? So if it's a matter of doing some high computation thing, lots of activities, you go for an actual Intel processor, something like this. But if your task is to, let's say, measure the temperature of a room and do something small, can go for a smaller microprocessor, kind of like this. So the best example that I kind of use is the air conditioner, because it does three things, right? I mean, if you think about it, the air conditioner, it measures the temperature of your room using a sensor. It checks if the temperature is too hot or if it's too cold. And the third thing is it switches on the actual cooling unit or the compressor or that thing you see outside and make sure that the room actually gets cool. It just does these three things. So to do these three things, it doesn't need an Intel i7 enormous like $100 processor, can afford to use a microcontroller. So drawing this diagram out, drawing the kind of schematic for this, it's a three-step process, right? So we have what's known as our inputs. In this case, it's the physical temperature of the environment. So there's going to be some kind of sensor connected. This guy is a sensor. This guy is going to give your inputs to the actual processor or the microcontroller. We'll call this the process. What the microcontroller is going to do is, it's going to check, is the temperature that's set, is it less than or is it greater than the value given by this guy? So this might give 28 degrees Celsius. That's coming from the environment temperature. And it's going to ask the question, is 28 bigger than 26? Is 28 less than 26? In this case, it's quite obvious. This is the answer. So it has a small piece of logic that runs, which switches on what's known as a compressor and starts the actual cooling process. So it's called the output of the system. So this three-step process that we see here is the kind of logic that works behind the scenes in a microcontroller. Additionally, you can kind of understand, I mean, it's not just asking the question and turning on the compressor. It also has to kind of, as a side task, show this information on the digital display. That's also another thing it does. Another thing might be receiving remote commands. So when we press the button on our remotes, the temperature up and down, it's sending a series of infrared signals. It's receiving them as an input, another input, and these signals are being processed by the microcontroller. So it's checking if you press the bottom button, and it's making this temperature go up or down. That's what it's doing. So that's like a side task the microcontroller has. And other features like, I mean, the sleep function, and you can have things like the cleaning function. All of these things are handled by a simple small processor inside the air conditioning unit. So that's what's known as a microcontroller. And the advantages I mentioned, unlike an Intel i7, the microcontroller or the MCU is very cheap, right? Cost is low. The performance is also low, but the thing is, for the task, that's pretty much enough. If you're running an AC, you don't need massive performance, so it's okay for the task. And another last thing is it consumes a small amount of power. So if we have a headphone unit again, and this works for 20 hours, you need something that has good power efficiency. And since a microcontroller does have good power efficiency, it's more suitable for an electronic component like a headphone. So that's how that works. And if we consider the headphone itself, this guy has a couple of things to do. It has to process the audio signals coming from the phone, which look something like this, right? And it has to convert them into sound that you can hear through your ears. The bass has to be perfect. The treble and all these other different aspects have to be perfect. Another thing is it can maybe detect the push buttons on your headset. So if you have a touchpad on your in your earphones or your headphones, just a single tap here might change the volume. It might move the track to the next track or something like this. So it has to be able to read user inputs. Another thing your headphones might do is ANC or active noise cancelling. So it has to continuously look at the sound coming from the environment. It's a microphone that I'm drawing. And it has to determine the exact signal it has to use in order to eliminate this sound. So by doing that, we get an output that looks something like this, right? Which is the sound has drastically been reduced, right? The decibels have been reduced by this ANC process. So taking this input, processing the sound, developing the waveform, and finally outputting the signal, the three-step process is pretty much what all of these components have in common. Whether it's reading the user input or the audio, everything, it's this basic three-step input, process, and output components that we have here. So that's what the microcontroller is basically doing. And if we have a look at what's known as the Arduino, it's a way for people just like you and me, like day-to-day people who are not advanced electronic engineers who studied at BScs at Harvard or anything. It's for everyday people to program a simple computer that does a simple thing like measure temperature and control a certain small circuit. It's a way for everyday people to engage in this activity. So people can go out and purchase what's known as a temperature sensor. They can purchase an Arduino. Maybe they can purchase a fan and they can code this logic. So they can detect our temperature from the environment. In an Arduino program, they can ask the question if it's greater than or if it's less than the temperature. Using that information, you can pretty much do anything. You can light up a bulb. You can send this to the internet. You can maybe turn on a fan. You can turn on a pump. That's up to you. But this logic is made accessible by this platform known as Arduino. So these boards you see here, these black color things in blue and with these pins and everything, maybe you can zoom into these things. These are different variations of the Arduino board. So these, in this case, it's mostly the same thing. I think it's known as the Arduino Uno, and the actual processing center is this black color bar here. So imagine this like your computer. You don't see the mouse, you don't see the keyboard, but what you do see are these black color lines which enable connecting things like temperature sensors to your Arduino. At the same time, you can connect an LED or an output to these black color pins and have, let's say the temperature is 28, you can turn on the LED in a different part of the Arduino or pin. So that's why we have this basic component called the Arduino. And again, this is meant for hobbyists, right? It's meant for hobbyists, artists, designers. It's not made for actually implementing a AC or anything. It's more of a way for general day-to-day people to engage in this activity of creating hardware and software so they can control things in their physical environment. Because no matter how much you can do software, it's not going to impact the real world unless you work with hardware, right? So that's why this Arduino is a kind of entry point for everyday people to get into this process of working with hardware and software impacting the real world. Okay, so moving on, we don't actually be installing any of these software because we are not going to be working with physical boards. But if you do plan on working with physical boards, you'll have to download the what's known as the Arduino IDE or the programming environment. Just like Visual Studio Code, the Arduino environment is responsible for uh, giving you the ability of programming this microprocessor. So determining the actual logic that goes into a system. So writing the piece of code that checks if it's 28 greater than 29 or determine the way we write that condition is done in this actual program that we see here. So in this case, this small program, it's not much, it's not doing much, but it's also following the basic philosophy that we spoke about before. It has an input, it has a process, and it has an output. Those are the three things it has. And in this case, it is a system developed to automate the process of feeding fish. That's why it's called fish stepper. Stepper stands for something known as a stepper motor, which is a motor that can turn, let's say, exactly 3 times. So it can dispense exactly 3 grams of food into the fish tank based on a given time, or maybe a button or something like that. So if we look at our basic philosophy diagram again, input, it might be, let's say, a button. The process is, it's going to work out the logic that will determine the controlling of the motor, right? So it's going to detect the press of the button, and your logic is going to be the actual thing saying that, hey, if the push button or if the button is pressed, let's start the motor. So this line of code is going to reside inside the Arduino or the microprocessor we have, and it's going to constantly keep checking if someone has pressed the button. If they press the button, then it's going to turn on the motor. That's what it's going to do. Okay. Now, the Arduino itself, I mean, I should probably mention this. The Arduino itself is working on DC current, as we mentioned. It's a tiny electronic component. It doesn't have much power, right? I mean, it doesn't work on 130 volts or anything. It's powered from a simple, in most cases, you can power it from your laptop, right? USB connection, remember it's 5 volts. So this component that we have, it can't power your massive water pump that you have that's going to pump out water from your well or anything, because this works on AC. There needs to be some middle component here. This middle component is known as a relay, and it's simply just a switch, right? So it's similar to what we discussed before, the transistor. Now this guy is going to give a signal, and it's going to say, okay, allow the 230 volt current that's connected here to flow through the relay. right? So it's going to make this process of flipping the switch automated. A person isn't going to come and press the switch button to make it go down. The Arduino is going to give a small electricity signal. Switch is going to go down, and the electricity from the actual wall is going to pass to your motor that we have here, or 230 volts is going to get passed once we give this small signal from the Arduino to our relay. So it's kind of the middleman that controls the flow of electricity from the wall, right? Okay. I mean, it works simply like a light switch, actually. If you think about it, it's simply just like the light switch you have at home, whether it's on or off. As soon as you switch this on, it allows the flow of electricity to the pump. The only thing the Arduino is automating is this light switch action. So instead of a person doing it, it's done electronically. The switch goes down and the electricity from the wall follows to the actual water pump or compressor, what have you. So that's the basic kind of process we have. If we just take this example of this fish stepper. And the code itself, you can see it's written in a language called C++. And the different if conditions and all these other components are written using basic loops. I mean, you can see there's loops here, it's conditions. And if you're familiar with this language, I mean, it's not too difficult. And there's also different parts that you might not be familiar with, like this part, for example. You don't necessarily see digital write in C++ because it's something related to the Arduino. Again, it's doing a certain thing. We might be able to do this as a demo when we start this walkthrough exercise. So let's get into that. Okay, so let's have a practical use and see if we can use an actual Arduino. But before that, I think we have to look at the diagram before that, right? Yeah. Okay, so this is, as I mentioned, what the Arduino is. It looks like this. It's a blue color PCB. And you can see a couple of things going on. So if I draw the diagram side by side, see if you can get this to work. So we have a blue color component like this. The component you see here in silver is used to connect to the computer and send the actual code or logic to the Arduino, right? It's connected to the computer through this port here. This guy right here is known as the 12-volt jack. We can power sort of high card components using this component there. The main heart of the Arduino, processing center of the Arduino, is this chip we see here, the black color chip that's shown here. That's the actual kind of CPU or processing center of the Arduino. These things that you see in black color, those are known as GPIO pins. So in this case, GP stands for general purpose, but the important part is their input and their output pins. So you can configure them. You can say, I'm going to take this pin right here, pin number 9, as an input. You can tell the Arduino, start reading information from the outside to this pin. Or if you wanted to, you can actually configure the same pin as an output. You can say, I'm about to send a signal from this pin to the outside world. So you can configure this option as an output or input depending on the logic that you put into your system. So you can see we have a large number of pins here, close to around, I think, 30, no, 20 or so pins. Some of them are known as digital pins, as you can see here. Some of them are known as analog pins. So I think we can kind of get into the basic exercise part of this activity. So if you are following at home, you can go to this website called walkthrough.com. I'll just paste it in the chat as well. right? And you can visit this website and just you have a couple of microprocessors here, STM32, Raspberry Pi, ESP32. These are more kind of advanced versions of Arduino, not specifically Arduino, but the advanced versions of microcontrollers. And so let's start with something basic. The Arduino Uno here, it's a blank sketch. That means there's nothing in it. It's pretty empty. And this is what it looks like. So we have our Arduino here. We have a code here. And this is our virtual kind of simulator. It's a virtual simulate. That means, I mean, it can't actually, you're not going to be actually able to light anything up, like a bulb, for instance, but you can simulate this on the computer and see what it will look like in the real life. So for example, if we are given a task of, here in this case, let's say, the most simple thing is blinking an LED. Right? So you've seen LEDs blink all the time before. On computers, you have blinking lights on different electronic items like ACs, for example, you might have a blinking light. And so we'll code the logic for how we can make a light blink using a microprocessor. So to start things off, we need an actual light. So to do that, we can press this plus button to add a simple LED that's shown there. And if you need any more information about this LED, you can press this question mark and it will show you the actual kind of description of what this looks like, right? And it will give you kind of understanding of what the pins are, the attributes like the color and all these things, and how to change it and other things. So one thing that I always mess up is the polarity here. So in this case, this is the plus. Let's just try it out. Okay, yeah. So the pin that you saw here that has a slight curve to it is the positive pin of our LED. So as you know, when we have an LED light, since this is an actual diode, it only allows electricity to flow in a single direction, right? Only one direction. So you have to make sure that you plug in your LED. You have to make sure to plug in your LED according to the plus and the minus, right? If you have a battery like this, you have to make sure that it's connected to plus and minus in order for this to light up. If you reverse the battery, it's not going to turn on. So just like that, our LED is connected to this case, 5 volts. The other side is connected to what's known as the ground or GND. If you draw the simple diagram for this, it looks a little something like this. So we have our LED somewhere here. Again, I'll draw it with standard circuit symbol. That's our LED. It's connected to our Arduino. And here it's connected to the plus. And here it's connected to minus. Plus and minus aren't labeled on the Arduino like this. They are labeled as 5 volts and ground, GND. That's how they're labeled on the Arduino. So that's what we have done here. But the problem with this setup is, I mean, it's always on. There's the blinking action. Why isn't it not blinking? The thing is, we haven't done anything in our code. And the other thing is, this guy is going to give a constant 5 volt supply to this LED light. And if we want to turn off the LED, we need to get rid of this 5 volts and make it 0 volts. if you reduce it to, let's say, 3 volts or 2 volts, the LED still might even turn off, but moving it to 0 completely gets the job done much more efficiently. So we have to get rid of this 5 volts. So instead of connecting the LED to the 5-volt continuous pin, which pretty much acts like a battery, we need to be able to give this LED a bit of logic. So we need to be able to say, okay, give the LED 5 volts, wait 1 second, give the LED 0 volts, wait 1 second, and do it all over again. So this effectively creates the blinking action, right? So we give 5 volts to the LED, we wait 1 second, then we give 0 volts to the LED, we wait 1 second, and continue this cycle forever. That's going to blink your LED. But you can't do this thing when it's connected to this constantly 5-volt pin. Because this 5-volt pin is permanently 5, you can't make it 0, because I mean that's what it's designed to do. So instead of connecting it there, can get rid of these lines and connect it to one of these GPIO pins. So in this case, I'll just pick pin number 8 and connect it to the positive terminal here. Negative side, I'll connect to the ground pin here, right? If I press the play button, nothing's going to happen. The reason is because we haven't told the Arduino what it should do with pin number 8. We haven't told it the actual logic. So if we try to write the logic here, let's see if I can just get this to work. We can start with setting. So first of all, we have to tell the Arduino that we plan on giving an output on pin number 8. To do this, there's a command known as pin mode. We say 8 and we just write output. That's pretty much it. So this is telling the Arduino that we plan on giving the output on pin number 8. We haven't actually given the output. They're planning on giving it. So get ready, right? That's what we do in this setup stage. So one common thing that happens in the Arduino is the setup part is used for initialization, right? So it runs only once, single time setup. But the actual blinking action, we want to run forever, right? We want to run it for an indefinite amount of time. So in order to run the blinking action forever, or the, what do you call, the lifetime of the program, we have to make sure it's inside the loop. So now we can actually start coding the logic. So if we go back to our diagram that we drew before, let's start with doing this first, giving 5 volts first. So in order to do that, there's a function in the Arduino called digital, right? It pretty much stands, I mean, you can understand it's digital, and it says the word write, which is given output. The pin number, we write 8, and we give an output of 5 or high. In this case, this will turn on this pin to 5 volts and start the flow of electricity through this bulb. You can also write here 1 if you like, but I'll just keep this high so it makes sense, right? Giving a high voltage there. You can probably imagine that's also low as well if we have a high. And the next part is to wait 1 second. So there's actually a command, simple command called delay. And we have to write 1 second in milliseconds, like so. In order to switch off the LED, we have to give 0 volts. That's what we'll do next. Digital, right? in number 8, low, and finally, we have to wait 1 second again in order to come back to the top. So that's what the basic program is doing. And if you run this, hopefully this should work. Yeah, so it's working. I mean, it's like this is the hello world of programs. So when you write hello world in C++, so what language you have, this is the Arduino version of hello world program. So what you're doing here is basically telling this microprocessor to give power to this pin every 1 second and take away that power after 1 second has passed, and do this process indefinitely over and over and over again. So, I mean, you can probably imagine you can change these to different values, 2 seconds, and it's going to keep this on for 1 second, keep it off for 2 seconds, right? So it's off for a bit longer now than it was before. Now, this is like a kind of a basic, really basic setup of what you can do with an Arduino. This is not, I mean, what it was intended for. This is step 0. It's where you start things off and get an understanding of what this is all about. So if you go to this website and have a look at a couple of examples, we might be able to see how, let's say, proximity. Okay, before we go to that topic, I mean, the basic logic is kind of, it makes sense right here. Now, in addition to simple LEDs or outputs, we can also get inputs to the Arduino. Or inputs are the actual important thing that we require, right? Inputs in this case can be given by sensors. They can be given by buttons. Those are also inputs. And those are primarily the main ones. And sensors, you have like literally hundreds of them. Can probably understand we might have temperature, humidity, maybe soil moisture, audio level. I mean, that's literally hundreds of sensors we can think about when we design these systems. So if you have a look at the actual sensors that we can, is there an example here? Okay, I don't think there's an example, but if we type Arduino sensors, well, this image is probably a good example. Okay, so there's all these different kinds of sensors you have. In this case, we have temperature, barometers of pressure, buzzers, those are outputs actually. Flame sensor is going to measure fire. The photoresistor is going to measure the amount of light we have. Humidity, I'm not sure why they have spelled it like this. And we might have the gas sensor is going to measure different amounts of carbon dioxide, carbon monoxide gases. Mercury switch is probably going to measure the tilt, I think. And so we have different things like the ultrasonic sensor as well, which is going to measure the distance from this sensor. Okay, so those are the type of sensors we have, and we have the actual ability of working with them on Boki as well. So if you just search for the ultrasonic, you can probably get a quick example here for an already built project using an ultrasonic sensor. Now you can modify this code, you can build this practically. You can go to the shop, buy an Arduino, buy the wires, buy a sensor, and connect it to the computer, download the software, paste this code inside, and what you'll be able to do is get the distance from the sensor. I mean, in this case, it doesn't make sense, right? Because we are doing this virtually, and the actual reading is going to be changed using this slider. But if you physically build this setup, it looks a little something like this. You can see that in this case, this sensor is sending out a signal, kind of ultrasonic signal. It's bouncing off this box we have here, and it's going back and hitting this other receiver on the other side here. So it's sending a signal here, it bouncing off this wall and coming back to this sensor. And you can see the reading is quite accurate. It's saying 8 centimeters, which is the actual value that's shown there. So that's a simple example of what you can do with an Arduino. And I mean, you might wonder what's the purpose of reading distances? I mean, what's the use of reading distances here? Well, if you look at a mobile robot, kind of like this, or if you look at the example that I had, I think in our slides even, right? We had this robot, I think, with this small kind of looking thing here. So that's the actual ultrasonic sensor that is using to detect how far it is from a wall. So it can detect a wall and make a left turn, right turn, instead of actually colliding with the wall. So that input or this logic or the information required to make this turning signal decision is given by this ultrasonic sensor. That's how it works. So the actual logic, I mean, you can probably understand by having a look at this. This is kind of what it looks like. So that's just a simple example of how an ultrasonic sensor can be used. And if we look into another simple example of how we can use logic here, let's come back to our previous project. And let's say now we want to make a project so that when a button is pressed, turn on the LED. If you want to do this, you can do it as well. You can go here, add a push button. It looks kind of strange. There's 4 different pins. Again, if you don't understand what the pins are about, you can just click this. You get a question mark, press that, and it will show you the actual layout of the button like so. So the actual layout works such that when you press this guy, it's going to connect this terminal and this terminal, kind of like a cross pattern. Not straight, but like a cross pattern. So in this case, we'll write a small piece of logic. Before that, we'll talk about the actual like kind of outline of what we're doing. So when the button is pressed, the Arduino is going to read a signal and it's going to turn on our LED light. Right? The actual logic or the actual functionality looks a little something like this. So to detect the press of the button, we actually have to give a voltage as an input to the Arduino. And again, we have a voltage source pretty close by. Voltage source, you can just find it here, 3.3 volts. You just get a line from here, connect this line to pin number, say 2. So the kind of system is designed such that when we press this button, the voltage flows through this line to this pin number 2. So the actual flow is not being done until we press this button. So at the moment, nothing is flowing. When we press it, it's going to flow electricity to this pin number 2. And that's when we need to turn on this LED. To do that, you need to tell the Arduino, start listening on pin number 2. Await the actual inputs on pin number 2. So we write pin mode, pin number 2, and we write input. Now, the second thing you might be wondering, what's input pull-up? This is a bit more advanced. I'm not going to go into the actual details of why we use that. But for now, I'll just use input here, right? So pin number 2, we are saying get ready to listen for voltages on pin number 2 or input signals. Get ready to listen for input signals or voltages. In this case, the voltage is 3.3, right? Okay, so then next thing we have to do is detect the actual button press, right? This is just saying get ready, but it's not detecting, right? To actually detect the button press, we can create a small variable, just like how you create variables in simple programming languages. Can call this variable, let's call it a Boolean value, and we'll call it is pressed. We'll set this to 0 for now. Okay. And we write what's known as an if condition, saying if the button is pressed, turn on the LED. But the thing is, just writing the variable isn't going to do anything. You have to get the actual information. So to get that, we use what's known as the digital read command on pin number 2. So it's going to await a digital signal and it's going to assign a value of true or false depending on if the signal is shown here at the terminal or not. So we can have this small piece of logic and we can write an else condition as well to turn off the LED. So these commands, that's to turn on the LED. This command is to turn off the LED. We don't need any delays here. And let's see if our code compiles. Yeah. So now you can see when we press this button, our LED sort of lights up, right? Since this is a virtual kind of thing, it does something strange at times. So, you can see it's like being continuously turned on. That's because this is a virtual software actually, and not because the code is broken or anything, but that's because it's mostly a virtual software, right? Because according to our logic, we read the voltage at this level. The voltage level is high. We turn on the LED light. It's low. We turn off the LED light. So this part is the actual logic behind the process. So there's a question in the chat. I'll just answer that. So one person is asking if there's a sensor to detect polythene specifically. And in this case, probably there is a sensor to detect polythene, but the thing is, it's going to be, I think, really expensive and it's not going to be able to detect just polythene, I think, right? Because if it's a metal versus plastic, that's quite easy. You can have a magnetic kind of sensor or a Hall effect sensor, it's called, to detect between polythene and plastic. But in your case, I think it's a different kind of question, right? Where you had detect plastic and polythene. So that might be quite a little bit more advanced. You'll have to search for it on Google actually. Things like this, plastic versus polythene. Plastic and metal, that's quite straightforward. But plastic versus polythene, even the differences for humans, I think is quite, it's different, right? Plastic is hard. Polythene is a different kind of structure material. So it's completely different in that regard. Okay, so I hope that answers the question. So this is a small kind of demo on how you can turn on this light using a button. Okay, so by doing this small exercise, even though it's simple and seems pretty useless, it goes through the entire process properly. So we have our input, the push button. It's connected to the Arduino. It processes it. We wrote our if condition saying if is pressed, turn on the LED. And we have the output, which actually lights up the bulb. So we have our complete flow given like so. So hopefully that kind of, you can play around with Walkby on this virtual environment. The advantage here is you're not going to burn any of these components, right? It's not going to cost anything if you burn these LEDs. On the other hand, if you purchase real Arduino, real LEDs, wires, these can catch on fire. These can probably, it's going to cost you some money if you don't know what you're doing. But an easy way to get used to this experience is to try it out virtually first and then do it in the real world. So this is just a basic setup we have here. But if you wanted to, you can pretty much create different kinds of systems using the different sensors they have here. So they have things like temperature sensors and all these different items. And they're using these to test our components before physically making them, right? Because just making the component virtually doesn't mean much, right? You're not going to gain anything unless you actually make the thing physically, right? Just doing this virtually is kind of silly because you're turning on a bulb using this virtual button. Unless you make the product physically, does it matter? This is just a testing platform in order to get used to the code, make sure it works, make sure the bulb works and the connections are properly connected. And then once you're done with all these things, once you're done checking software and everything, then you can buy the actual components, connect it according to the same way, paste the code in, upload it using the Arduino IDE, upload button is here, and run the device physical, right? So that's what this platform is intended to do. Okay, so I think with that, I think we have covered up most of the important parts of this topic, Arduinos and electronics. Mm, so the actual coding part is given here. It's what I wrote in the program. So the instructions are given here. Okay, so I think that should help you kind of get an understanding of how this works. And again, these slides are meant for the physical kind of aspect of this. That's why you have all these, the actual ID and everything working. But on walkby.com, you just have to press the play button and it pretty much works. Okay, so common syntax errors and common mistakes you get. We go through this one by one. There's some memes here, but you can probably understand this if you're into programming. You know that just having a simple case letter or uppercase letter or missing symbol, you get an error. In Python, it's different entirely. You have a space, you get errors as well. But that's an error like that. And here's another one, which is forgetting to return from a function. So that's why sometimes you don't get information that you expect. So those are just a couple errors. You can't list the errors because those come with experience. So you have to do this process multiple times again, test, and test again until this stuff works and is reliable. That's what this whole engineering through hardware process is like. Because unlike software where we can just press Control Z and go back, in this setup, if you burn an LED or if you burn a wire, you can't just go back and press Control Z because it's done physically reversible damage to a physical item. So that's the difference between. Okay, so if you go crazy and if you have multiple different LEDs, if you have plenty of time, you can make something like this, which is not too useful, but it kind of demonstrates the concept of logic and controlling outputs. If you do this and replicate this version on a 2D panel onto 2 million LEDs, you get pretty much a mobile display or a computer display. That's what a display is, right? It's controlling LEDs, millions of them, to show different colors, shapes, and everything, just like the image that you see on the screen right now. Okay, so these are, I think, a couple other things you can see. I mean, temperature, light sensors, motion sensors are available. Actuators, in the sense, we have motors, we have thing known as servos, and you can build simple robots, implement simple robotics. You can connect this with the internet actually. So you can connect Wi-Fi, send this information like temperature to your server, and maybe monitor the temperature from anywhere on the planet. That's another thing you can do using an Arduino, because it has internet capabilities, not on this Arduino, but there's different types of Arduinos, different types of microcontrollers, which do have internet capabilities, which you can purchase and use. So this is what I kind of meant. So when you press the on button, instead of having a button close by the Arduino, this could be on the other side of the planet. And since it's connected with, let's say, Wi-Fi, you can turn on this LED from somewhere else. In this case, it's Bluetooth, so it has to be nearby, but the point is still the same. And you can have things like a display and all these other different things. So the ultimate, I mean, output looks something like this, where you have a smart home which has the ability of detecting a couple of different things. So when a person is at the door, it might switch on a light. If the door is opened before it's unlocked, it might sound an alarm. Things like this you can program into your Arduino, but in the real world, it's done using a much, much more advanced microcontroller, which is not the Arduino. But as a gateway into this, world of programming and sensors and outputs, Arduino is a good place to start. So that's why we do this Arduino thing. Okay, so with that, I think I can kind of conclude the session and wind things up. So I hope that everyone is watching, either if it's a recording or if you're live, that you got a good understanding about hardware, how it integrates with software, and I hope you kind of got an understanding how you can practically kind of implement this, the process, the input, the output, and visualize it using these free tools that we have on the browser. So the ultimate goal, I mean, just watching this isn't enough. You have to get hands-on with these components, with the Arduino, connect the wires. You have to run into the errors, the problems, the troubleshooting, all those things. That's only when you can understand how complex engineering with hardware is actually like. So you can probably imagine, if building a small robot is this difficult, how difficult it must be to build something like this. Because this has millions of components, and the millions of components have the same issues that your Arduino might have, with loose connections, with other things like wrong programming logic, all these things. This larger thing has all these problems as well. But the only difference is it's the amount of engineering and time you spend working on the system. Okay, with that, I think I'll wrap up the session and we can, I think, conclude this. So I hope everyone kind of got an understanding about Arduino, about microcontrollers, about programming and logic. And with that, I think I can wrap up the session, right? Yeah. Okay. So thank you for everyone participating. I'll stop.
Excuse me, sir. I got a question.
Yeah, okay. So I forgot to mention, if you have any questions, yeah, you feel free to ask them. Yeah.
Yeah. When you power up a servo, will you use the GPIO pins or something else on the microcontroller?
Okay. So in this case, when we have this in the case of the Arduino, you can actually connect the servo motor. Let's have a look at the servo motor for those that haven't seen it. You can actually connect the servo motor directly to the Arduino and it will work. But most of the time, you have to use what's known as a servo motor driver. This is much more kind of effective in operating the motor because it makes sure that the Arduino doesn't kind of draw overcurrent in order to power the motor, because the motor is going to use a lot of electricity. It's going to use a lot of amps. And if you have lots of amperes moving through the Arduino, there's a probability that it might get burnt. So it's best to have what's known as the servo motor driver as the middleman when you're driving a motor or servo motor, right? But for an example and for a practical small example like on Walkvi, you can directly connect the servo to the Arduino. If you just Google servo and then Walkvi, you'll probably get a good example here
The
of a
container,
servo kind of like this, right? So in this simulation, by turning the knob, you can see it's going to change the angle of our servo motor, right? So everything here is directly connected. But if you make this in real life, most likely go for a servo driver, right? Servo motor drive. So I hope that answers your question.
okay.
Okay. So any other questions you have? Anyone?
Excuse me, sir.
Yeah.
So use a
Which sensors are essential for the health mirror?
Sorry?
Which sensors are essential for the health mirror, sir?
Can you type up the question? I think it's not clear. Type the question in the chat.
Which sensors are essential for the health mirror? So like that, heart rate sensor, ECG.
Okay. So to measure health related things, there's actually a couple of sensors. So one of the things you can use is the heart rate sensor. It's a small sensor that you can kind of put your finger on top of. So you put your finger on top of this sensor, it scans it with a light, and depending on the change of intensity of the reflected light, it's going to calculate the heart rate of a person. So it works, it doesn't detect the change of movement, it detects the change of kind of light intensity once it gets reflected back. So I think that's a good example here, probably to kind of understand this process. So this is kind of what it looks like. So it will have there's a small light here. It will illuminate the finger and the reflected signal will change, the level of the reflected light will change based on these micro movements of the blood vessel. Right? So actual setup looks something like this, I think. So you can measure the heart rate like that. That's just one of the sensors. There's things like the body temperature sensor as well. Right? You have different kinds of
Okay.
things like that. Right.
So the USB Arduino board is used for health mirror.
There's different types of Arduino boards actually. So you can get this Arduino Uno, which is quite large, but there's a thing called Arduino Mini, and there's a thing called Arduino Mini Pro. You can see all of these look quite different. These are much smaller, right? You can see. And there's things like ESP32C3, which are even small, right? So it's only this big, right? So this is how small it is. And even on this thing, you can see it has different pins, input outputs. The microprocessor is here. USB connection is here. So you have different kinds of microcontrollers that you can buy. They do the same thing, but this guy has Wi-Fi built in, Wi-Fi and Bluetooth built into this small chip here. Right? The Arduino Uno doesn't have Wi-Fi or Bluetooth. You need to get a separate module in order to use it, right?
So we will use Arduino Wi-Fi, sir, R3.
Yeah, so if you want, there's the Arduino Wi-Fi version is also there. So the new version
Yes,
of the
sir.
Arduino actually has Wi-Fi built in. You don't need to buy any other modules. You have to just purchase the latest version of the Wi-Fi Arduino, right? Okay.
So how to connect this board in the laptop, sir?
Quite straight. You just have to connect this Arduino that's shown here to the USB connector
Yes,
here,
sir.
right? Arduino.
Yes, sir.
So you can see that it
So we
comes
use
with a
a USB, sir.
USB cable and it's connected to here,
Yes. Okay, sir.
right? This is where you connect it. So, I mean, you can find dozens of tutorials on this on YouTube. You can find step-by-step instructions. They go through the code, how to connect the sensors, the pins, and special tips you might have. There's lots of videos on YouTube on how to do these things. But get a kind of rough understanding. And there's this website called Last Minute Engineers. And you can pretty much find any kind of sensor on this, most of these sensors, and kind of look at how they work. So the ultrasonic sensor, for example, if you go through this has a huge kind of article explaining the principle, how the ultrasonic sensor works, how the code is working, how the sensor processor, the microcontroller on this sensor is working. All these things are shown in this website. So all of these like connection diagrams, everything is shown in this website called lastminuteengineers.com. Right, so
Okay.
just browse through this. You can pretty much find. I'll just put it in Zoom as well.
Okay, sir.
Okay, so with that, I think I can conclude the session. So thank you to everyone for joining, and hope you have. Right.
Sir,
Okay.
excuse me, sir.
Yes.
Can you give me the contact number for any doubts, sir?
Probably you can contact me on my email address, right? Yeah.
Okay, sir.
Yeah. So just if you have any emails, just you can contact this email, right? Okay.
Okay, sir.
Right. Okay, then with that, I will end the session then. Thank you for everyone. Okay.
Okay, sir.